In this lesson, we want to consider the thermodynamic principles that govern biochemical systems and processes. You will apply these basic principles throughout this course. All living cells require energy to function, and the sun is the ultimate source of this energy for our planet. As we will see later, organisms capable of photosynthesis capture the energy of sunlight and convert that into a chemical form, ultimately into the synthesis of carbohydrates. Organisms such as humans that are not capable of photosynthesis rely on the carbohydrates produced by those photosynthetic organisms. As we continue our study of biochemistry, and especially in the section on metabolism, we'll see that many cellular processes involve the transfer or movement of electrons. In basic chemistry, we learned that when an atom loses electrons, it has been oxidized, and that reduction is the gain of electrons. A popular mnemonic is the phrase oil rig. Oxidation is loss and reduction is gain. The principle applies also in organic or carbon-based systems, like those we encounter in biochemistry, but it has more to do with the distribution of electrons within the chemical bonds rather than the net charge. This is often demonstrated by Lewis dot structures, like the one shown here. We'll return to this subject later. For now, just realize that redox chemistry has much to do with biochemical processes. Thermodynamics is the study of the transfer and transformation of energy, and the term literally means heat changes. Note that for any change of a thermodynamic component, such as the change in the Gibbs free energy, or delta G, we subtract the value of the initial state from that of the final. In other words, the change is equal to the final minus the initial. If the change in free energy is a negative value, this means that there is less energy in the system in the final state, and that therefore energy was released to the environment. In this case, the reaction was spontaneous. If instead the energy change was positive, then there was more energy in the final state, and therefore energy was added to the system. Since energy had to be supplied, the change was not spontaneous. A familiar illustration is that of a ball rolling downhill. After the initial start, the ball rolls downhill spontaneously. Notice that the ball is at a lower energy level at the bottom of the hill as compared to the top, so energy was released. By analogy, there are chemical processes that also release energy. That is, the change in Gibbs free energy is negative, and the reaction is spontaneous. Much of what we'll consider throughout the semester has to do with energy changes such as these.